Welcome to the Copperfield Electric Podcast.
Yeah, this is one of those topics that catches basically everyone off guard.
It really does, because, if you just bolt 20 state-of-the-art solar panels to your roof today, there's a very high probability the city inspector is going to shut your entire project down tomorrow.
Oh, absolutely. Shut it down cold.
Right. And we always imagine the end result of home improvement, the gleaming silicon on the roof, the lower utility bill, that whole feeling of energy independence. But today, we are doing a deep dive into the hidden bottleneck of the modern home.
The part nobody really looks at until it's a problem.
Exactly. The unseen gatekeeper that dictates exactly what your house is capable of doing. The electrical panel.
It's literally the one piece of infrastructure that physically limits the green energy transition for, millions of homeowners right now.
And for this deep dive, we're pulling from a really comprehensive set of technical materials provided by Copperfield Electric.
Yeah, they're a trusted, family-owned, 24-hour electrician service based in Orange County, California.
And their service footprint is massive across Southern California. They are handling these exact electrical upwards day in and day out in places like Irvine, Anaheim, Santa Ana.
Costa Mesa, Newport Beach, Tustin, all over that area.
Right. If you are in that region, they are the people running the calculations and basically keeping the lights on.
And the documentation they provided gives us a really stark look at the reality of residential electrification. Because people tend to treat solar installation as, well, like a roofing project.
Right, like putting on new shingles or something.
Exactly. You put panels up, you run a wire down, and boom, you're suddenly generating your own power. But the physical reality of how that power integrates into a house built 30 or 40 years ago, that is where the real friction lies.
And that brings us straight to the core issue. Before anyone even looks at the roof, the critical first stop has to be the side of the house. Or the garage. The electrical service panel.
The central nervous system of the house.
Yes. Because every appliance, every outlet, your HVAC system, and eventually the solar circuit itself, it all draws power through the main bus bar inside that panel.
The bus bar is really the structural backbone we have to focus on here. It's an engineered piece of conductive metal, usually copper or aluminum.
Okay.
And its job is to distribute the current to all your individual circuit breakers. But when you install solar, that busbar suddenly has to manage power from two entirely different directions simultaneously.
Which it wasn't originally designed to do, right?
Right. You have the traditional utility grid feeding power in, and your new solar energy system pushing power in. It has to handle this continuous two-way flow without exceeding its thermal capacity.
Okay, let's unpack this for a second, because this is where the intuition falls apart for a lot of people.
Sure.
The panel is like a funnel. But wait, if my house is running perfectly fine right now with a 100-amp funnel, and I add solar panels, which are generators, right? They make electricity.
They generate power, yes.
So why does that suddenly make the panel dangerously crowded? It feels like adding solar should relieve the stress on the system because the house doesn't have to pull as much from the grid.
Yeah, it's a completely counterintuitive concept. You naturally assume electricity behaves like water relieving a drought, where any extra supply is just a good thing.
Exactly. More water, less drought.
But electrical engineering is about managing potential energy and, more importantly, thermal limits. The issue isn't just about what your house is actually consuming at any given second. It's about the total potential current combining on that busbar from two different sources at the exact same time.
Because the solar power doesn't just bypass the panel to get directly to the fridge.
No, not at all.
It all converges on that one strip of metal.
Exactly. And the physical metal of the busbar is only rated to handle a specific amount of current before electrical resistance causes it to heat up.
Ah, so it's a heat issue.
It is entirely a heat issue. If you push too much combined amperage across it, the metal gets hot, the insulation on the wires begins to melt, and you are looking at a catastrophic thermal event.
A fire.
A fire, yes.
Yeah. And the historical context here is what really makes this a crisis for places like Orange County. If you look at the tract homes built throughout Southern California in the 1970s and 1980s, the builders sized those electrical panels for the expected loads of that era.
Which were tiny compared to today.
Right. A house back then might have had an electric stove, a water heater, maybe central air conditioning if you were lucky, and just a few dozen incandescent light bulbs.
The peak load demands were fractionally what they are today.
Yeah.
A standard panel installation for a typical residential build before 1990 was usually 100 amps.
Just 100 amps for the whole house.
Yeah. And at the time, An electrical engineer would look at that and determine 100 amps provided plenty of headroom.
Not today.
Today, a 100 amp service is barely enough to run a standard modern household, let alone integrate aggressive new technologies.
Because we're taking that 1980s infrastructure and demanding its support, two level 2 electric vehicle chargers in the garage, a high-efficiency electric heat pump, an induction range, a smart fridge.
Right. The baseline continuous draw of a modern home is just skyrocketed.
Which means the 100-amp panel is a massive bottleneck. But, and this is crazy to me, even if a homeowner goes out, checks their panel, and sees it's rated for 200 amps, they still can't just call a solar company and start bolting things to the roof.
No, definitely not. You can't pull a permit based on a quick visual inspection. You have to prove the system can actually handle it mathematically.
But even before we get to the math, our sources from Copperfield Electric highlight some physical warning signs that homeowners can spot right now.
Yeah, there are a few immediate red flags.
Like if you open your panel and see it's rated at 100 amps or less, you're almost certainly facing an upgrade.
Almost guaranteed, yeah.
And if your breakers are already tripping frequently under your current load, the panel is physically telling you it has reached its thermal limit.
Exactly. Age is another massive factor. If the panel is older than 25 years, the internal components, the bus bar, the breaker connections, they've all experienced decades of thermal expansion and contraction.
They just wear out.
They degrade over time, yeah. You also have to look for physical space. A new solar system requires its own dedicated 2-pole breaker.
So if you have 0 open slots.
You can't just magically squeeze one in. It doesn't work like that.
Right. And finally, there are those legacy panel brands with known documented safety issues.
Yes. Brands like Federal Pacific or Zinsco.
The ones that fail to trip during overload.
Exactly. Those have to be replaced regardless of whether you're adding solar or not. They're just flat out dangerous.
Okay, but assuming you don't have those obvious physical red flags, we hit that mathematical proof you mentioned earlier.
Yeah.
The load calculation.
Right, the load calculation.
Yeah.
This is where the professionals really have to step in.
So what exactly is it?
It's when a licensed electrician evaluates your home to calculate exactly what your panel requires to safely support the solar array, your current baseline usage, and any future heavy loads.
It's kind of like getting a tailored suit instead of just buying off the rack. It takes all the guesswork out of the equation.
That's a great way to put it. A proper load calculation involves measuring the square footage of the home, the wattage of every major fixed appliance, the heating and cooling loads, and applying something called a demand factor.
Or in band factor.
Yeah. It acknowledges that you are never realistically running your oven, your air conditioner, your vacuum, and your EV charger all at the exact same millisecond.
Okay, that makes sense.
But it builds in a strict safety margin to ensure that even on your home's absolute heaviest usage day, the main bus bar will not overheat.
Now, what's the danger of skipping this step and just hoping for the best? Because the friction here is that homeowners often want to skip this to save time or, a few $100.
Well, they assume that if they hire a solar company, the solar company will just handle all that back-end stuff.
Right.
But skipping the formal load assessment almost always guarantees a failed inspection from the city or the utility company.
Yeah.
And the really brutal part is when that inspection actually happens.
It doesn't happen during the planning phase, does it?
No. The city inspector shows up at the very end of the project.
Oh, no.
The installers have already been to your house. They've penetrated the roof, mounted the racking, bolted the panels down, and run the conduit all the way down the side of the house.
Oh.
And then the inspector opens your outdated panel, realizes the bus bar capacity is mathematically overloaded by the new solar breaker, and fails the project on the spot.
So you end up with thousands of dollars of state-of-the-art solar tech just sitting uselessly on your roof.
Completely useless.
Yeah.
You are legally forbidden from turning the system on until you hire an electrician, upgrade the panel, pull a new permit, and undergo a completely new inspection.
That is an administrative nightmare.
It grinds the entire transition to a halt. And the reason inspectors are so incredibly strict about this brings us to the hidden math that actually governs the modern energy transition.
Right, the rules.
The code isn't arbitrary. It is incredibly specific regarding how much current can interact on that bus bar.
And this is something I found super interesting in the sources. When you dive into the forums or talk to solar salespeople, you'll inevitably hear them throw around a term called the 20% rule.
Right. You hear that everywhere.
But here's where it gets really interesting. According to our sources, that is actually a mislabeling of the code, and it causes a ton of confusion. The actual regulation is the National Electrical Code's 120% rule.
Exactly. The NEC's 120% rule dictates the interconnection limits for energy generation.
How does it actually work?
It states that the combined rating of the main utility breaker and the new solar breaker cannot exceed 120% of the busbar's total rating.
Okay, let's run those numbers because this is the exact math the inspector uses to pass or fail a home, right?
Yep. This is the exact formula.
So if you have a standard modern panel, the bus bar inside is rated for 200 amps.
Right.
Under the NEC's rule, we take that 200 and multiply it by 1.2. That gives us a strict cap of 240 amps.
Right. That 240 is the absolute maximum potential current allowed on that piece of metal from all sources combined.
Okay. Now apply the breakers to that limit. Your main breaker, which controls the grid power coming in, takes up 200 of those amps.
Yeah.
Subtract that 200 from your maximum allowance of 240, and you are left with exactly 40 amps.
So on a standard 200 amp panel, you are only allowed to install a solar breaker that is 40 amps or less.
Wow. So what does this all mean if someone needs a much bigger solar array that requires more than 40 amps? Like, what if your load calculation says your massive new solar array needs a 60 amp breaker to send all its generated power back to the grid? Are they just out of luck?
If you try to just put it in, you fail outright.
Because of the math.
Because of the math. The inspector will not sign off because a 60 amp solar breaker plus a 200 amp main breaker equals 260 amps.
Which is 20 amps over the limit.
Exactly. It exceeds the 240 amp legal limit of the bus bar. The risk of fire is just too high.
Now, I've read about a workaround for this in the provided text called derating the main breaker. But I've got to say, it sounds like you are intentionally throttling your house's power supply just to satisfy a math equation.
It does sound like that, yeah.
If I decorate my main breaker, aren't I just starving my house of the grid power it needs to run, like the air conditioning on a hot day?
It sounds like throttling, but if the load calculation is done correctly, you aren't actually starving the house at all.
How so?
This is where the difference between theoretical capacity and actual usage comes into play. Let's say your load calculation proves that your specific house, with your specific appliances, never actually draws more than 150 amps from the grid, even on the hottest day of the year.
Okay.
If that's true, you don't actually need that full 200 amp main breaker.
Oh. So the electrician can legally swap out the main 200 amp breaker for a smaller one, say a 175 amp breaker.
Correct. And remember, the bus bar's maximum allowed limit is still 240 amps.
Right.
But by dropping the grid's main breaker to 175, you subtract that from the 240 limit. You are now left with 65 amps of available headroom for your solar system.
That makes total sense. It's like widening your driveway or reassigning the lanes on a highway. The physical highway didn't get any wider, right? The bus bar is still exactly the same size, but you took one lane away from the incoming grid traffic because your house didn't actually need it, and you dedicated that lane to the outgoing solar traffic.
That's a perfect analogy.
Yeah.
You satisfy the safety code without having to tear the panel off the wall.
It is a brilliant engineering workaround.
It really is.
Yeah.
But derating has its limits.
Right. It can't fix everything.
No. If your house genuinely pulls a massive amount of power, or if you are stuck with an old 100 amp panel where derating is mathematically impossible because the baseline load is just too high,
Then you're out of options.
you have exhausted the workarounds.
Yeah.
You have to move to the ultimate solution, which is a full electrical panel upgrade.
And this is where we really have to look at the practical and financial realities of a massive home improvement project, because it's not cheap.
No, it's an investment.
According to the data from Copperfield Electric, a straightforward upgrade from an old 100 amp panel to a modern 200 amp panel typically costs between $1,800 and $4,500.
And that range includes the necessary permits and the city inspections, which is good.
But the financial cost is only one factor. The logistical timeline is the other big one, right?
Absolutely. Homeowners, especially those in Southern California, really have to budget time for utility coordination.
Yeah.
You aren't just dealing with a private electrician, you are dealing with Southern California Edison.
Right, because the electrician has to completely disconnect your house from the grid to swap the panel out.
Exactly. And because of that, SEE has to be heavily involved.
The electrician can't just snip the wires from the street while they are live.
They absolutely cannot. That's incredibly dangerous. So before SEE gives the final approval to re-energize the new panel, They often need to inspect the service line.
The line coming from the street.
Yeah, the lateral wire that runs from their neighborhood transformer directly to your house. In a lot of older neighborhoods, that service line, whether it's overhead or buried underground, was only sized to deliver 100 amps.
Oh man, so SCE might have to physically upgrade their own infrastructure just to handle your new 200 amp capacity.
Yep. And if that line is buried under your lawn, you might be looking at trenching.
Wow.
It becomes a highly coordinated effort between the electrician, the city inspector, and the utility company.
Now, when people hear that an electrician is coming to upgrade the panel, I feel like the immediate fear is that the walls are going to be torn open and the entire house has to be rewired.
Oh yeah, that is the most common myth we see by far. But thankfully, it's completely unfounded.
Okay, that's a relief.
The electrical panel is really just the central distribution hub. Upgrading it usually does not require rewiring the branch circuits that run to your bedrooms, bathrooms, and kitchen.
So they aren't tearing out drywall in the living room.
No, not at all. The electrician is simply replacing the main box, installing a new, heavier bus bar, and putting in new breakers.
The only time they'd need to touch the internal wiring is if they open the walls right there and find existing damage, right?
Right. Or if the house has ungrounded legacy wiring, like knob and tube, that completely fails modern safety codes. But assuming the copper in your walls is standard, it stays exactly where it is.
The focus remains entirely on that entry point, like we said, widening the driveway, not rebuilding the roads inside the neighborhood.
Exactly. And this highlights a much broader strategy regarding home improvement. Upgrading to a 200 amp panel really shouldn't just be viewed as a tax you have to pay to get your solar permit approved.
It's bigger than that.
It is an active step in future-proofing your home.
Because the overarching push in residential building right now is full electrification.
Yeah.
Everyone is moving away from gas.
The transition away from fossil fuels means the electrical demands on residential homes are just going to skyrocket over the next decade. When you upgrade that panel to 200 amps, you are creating the necessary electrical headroom for continuous heavy loads.
And we aren't just talking about running a toaster for 3 minutes.
Oh, no, we are talking about level 2 EV chargers that pull 40 to 60 amps continuously for 8 hours every single night.
You're talking about electric heat pumps replacing gas furnaces, running continuously to heat the home all winter.
Exactly. You're looking at hybrid electric water heaters and eventually adding stationary battery storage systems alongside the solar array so you can island your home during a grid blackout.
And literally none of that is possible on a 1980s 100 amp bus bar.
Which is what makes the timing of the upgrade so critical. Doing the panel upgrade before or simultaneously with the solar installation is the only pragmatic approach.
Because if you just scrape by, right.
Yeah, if you manage to scrape by with a disrated 100 amp panel today just to get a small solar array installed, you are painting yourself into a corner.
Right. Because if you buy an electric vehicle 2 years from now and suddenly realize you need that level 2 charger,
you're back to square one. You have to hire an electrician all over again, pull a new permit, coordinate with Southern California Edison again, and undergo another round of city inspections.
You end up paying for the administrative friction and the labor twice. That's just throwing money away.
Evaluating the total future load of the house right at the beginning is the only way to avoid that trapped capital. Get the load calculation done, understand your household's energy trajectory for the next 10 to 15 years, and upgrade the infrastructure once.
Because at the end of the day, upgrading your electrical panel is the necessary structural backbone of a safe, modern energy system. You simply cannot run the high-tech, electrified home of the future on the electrical infrastructure of 1985.
The physics just don't allow it.
They really don't. And thankfully, professionals like the team at Copperfield Electric are available 24/7 to bridge that exact gap. They do the load calculations, pull the permits, handle the coordination with Southern California Edison, and ensure the engineering actually supports the technology you want to use.
And, knowledge is most valuable when it's understood and applied. Now that you understand the mechanics of thermal limits, the bottleneck of the 100 amp system, and the strict math of the NEC's 120% rule, the next step is straightforward. Go out to your garage or the side of your house. Open the door to your electrical panel and locate the main breaker. Look at the number stamped on it. Taking those 5 minutes to see your current capacity is the smartest first move you can make.
Go check the capacity. Get ahead of it. But as you are standing there looking at that gray metal box, I want to leave you with one final thought.
Oh, here we go.
We've spent this entire deep dive looking at the micro level, right? how individual older tract homes need these 200 amp upgrades to safely handle solar power and electric vehicles without overheating.
Right.
But zoom out for a second. If every single house in a massive 1980s Orange County neighborhood suddenly upgrades to 200 amps and they all simultaneously start pulling massive loads to charge their cars at 6:00 p.m. or pushing massive amounts of solar back to the grid at noon,
Oh, man.
how in the world are the overarching aging neighborhood transformers and utility grids going to handle that unprecedented bidirectional shift in power flow?
Now, that is an engineering crisis for another day.
It really is. Until next time.